first of all, thanks a lot for attending this session on infrastructure for deep learning in Apache Spark. So my name is Hyong, and together with Karthik, hopefully this 40 minutes will be useful to you if you're thinking about using deep learning on Spark. And most of the time we get asked a lot after a session on where to find the slides. So we put it up front, and so if you go to this link, this will actually get you to the slides. I'll wait for everyone to take a picture. A few more. Okay. Now, so this talk, this is how we're going to look at the agenda. We're going to start off with, like within the Spark community, and in fact, this is my first time at the Spark AI Summit, but we've been following some other related big data conferences for a while. If you look at a lot of the sharings from many of the companies, whether it's a startup or Fortune 500 companies, or even at Microsoft, we've seen this evolution of, people starting off with a data or big data infrastructure. And over the recent years, because of the need for doing machine learning, and more specifically deep learning as well, on thinking about how you could then do both deep learning as well as big data on the same infrastructure, and what are the considerations. And we went through the same kind of evolution at Microsoft, and Karthik used to be from the Bing team, and so he's going to share some of his experience later. And then we're going to move on to talk about the machine learning workflow, just to ground everyone so that we have in mind the same workflow. We're going to introduce a little bit about deep learning and some of the computing needs. And finally, we're going to share some of the challenges and some of the solutions that we found over the years. And hopefully this sharing is useful to the community. And of course, we're going to touch a little bit about what does it mean to have being able to handle both data and machine learning workloads on using Spark. And we're going to end off with some discussions around ML pipelines. Now today, if you look at the landscape, right, many of us, like I come from a data warehousing background and evolved into doing big data, and more recent years doing machine learning and deep learning. This is essentially the different kind of organizational data that we have to deal with, right? Whether it's data that's sitting in a data warehouse, or getting to a point where you have unstructured data sitting in various kinds of data stores. Today, we hear a lot about all these transcripts that happen during a call for a call center. How do you go about processing them? Because somewhere inside that data lies the insight that might help you improve your product, lies the insight that might help you understand your customer better. Right? To more recent years, there's been more and more exploration or even production system being done at various companies, right, on being able to deal with products and images, or even dealing with video files, right? And of course, if all these are organization data, it sits on some infrastructure, right? And so then we switch gear a bit and look at a typical machine learning process, and you'll see different versions of this at various conferences as well. But just to ground everyone to the same frame, you have a preparation stage where you do data preparation, and if it's image kind of data, you might do some augmentation. If it's audio or video kind of data, you might also do some preparation as well. And then you have a platform for experimentation, right? And of course, in order for you to run lots of experiments every single day, you need to be able to train and test your models using an infrastructure that scales, right? And once you have done that and you get to a point where you have the models that you want, you will register and you will manage, you will register the model, and so that it's on the way to production. But at the same time, you also want to deal with the model lifecycle management and so on and so forth, right? And therefore, deployment is a huge thinking as well. And so if you look at this, machine learning workload, big data workload, and deep learning workload, if you want to mesh them together in the same infrastructure, there are several considerations, right? And we're going to get to this in the talk. But before we get to that, if you look at before 2017, right, how long does it take to train a ResNet 50 on the Imagenet dataset? It took about 14 days, right? That was before 2017. But 2017, 2018, up to today is really exciting. It's because it got from 1 hour to 30 minutes to 15 minutes to 5.5 minutes, right? And all this, you see the different companies that's participating in this kind of challenges, right? Ranging from both GPUs as well as CPUs. But in 2018, it got down to 2 minutes. And in 2019, just a few months ago, or in fact this month, right, it got down to 1.5 minutes, right? And of course, you could say, well, these are all benchmarks, if you will, that has been accomplished on huge infrastructure. But just about after this last feed that happened in 1.5 minutes, which happens on a distributed set of nodes, right, in a cluster, somewhere in Asia, one of the companies dealing in real estate demonstrated that on the Azure cloud, using a single node, an ND series machine, they were able to finish Imagenet training, right, in about 1 hour, 30 minutes, right? And so today, this kind of power is readily available to every one of us in this room. And so that's also one of the reasons why when we start looking at combining big data, machine learning, and deep learning workload, and you'll see a lot of these sessions in this conference, it's super important to start thinking about how you evolve your infrastructure. And so what are the considerations for deep learning at scale? Well, one is CPU versus GPU. Two is, well, should you have a single versus multi-GPUs? And once you have all this figured out, you should think about, well, should this be a message passing interface or MPI-based or non-MPI system? And underneath interconnecting all this node, should it be InfiniBand? Should it be Ethernet? Or should it be some sort of accelerated networking infrastructure? Right? And what you see on the right is essentially some of the work that our team has done in trying to compare these different kinds of differences. The link below actually shows you deeper details on the comparison that's done. But then, if you look at all this, whether it was the Imagenet feed that I was sharing with you, and those different kinds of considerations, there are practical things that we all need to do when dealing with training machine learning and deep learning models at scale. One is there are dependencies, right? There is packages that you need to load at runtime. There's packages that you need to deal with. And then you have to think about, well, how do you handle failure? How do you secure access to the data where huge progress has been made within the big data space, and so on and so forth? And once you have done all that, if you're going to do a distributed machine learning or deep learning job, how do you gather the result and then being able to further process the result so that you can present to the end user or consume in some downstream production system? And finally, you start looking at, well, as the workload grows, just as big data workload has been growing really rapidly, how do you go about scaling the resource or even trying to distribute the data in a smart way? And last, of course, you want to be able to schedule this job so that you can keep running them and so on and so forth. Right? So these are practical things that you have to deal with. And so if you look at it, I'm not going to go too much into the details for this. This is essentially the difference between machine learning and deep learning in one slide. Not the best slide, it's not meant to be exhaustive. But the point is, today, using an infrastructure like Apache Spark, right, you could now be able to do both big data, machine learning, and deep learning workload at scale, right? And so things you have to grapple with as a data scientist is, well, you could be using TensorFlow, you could be using PyTorch, you could be using any of these libraries that's out there. And so if you put all this together and you look at the design choice that you have to grapple with when thinking about evolving your infrastructure is the following. Today, you could train your models, or whether it's machine learning or deep learning models on your laptop. In fact, on the way here from Seattle, right, in the cloud, literally when taking the plane and in the cloud, I was training a model preparing for this talk on my local machine, right? But you want to get to a point where you could then scale a lot of the work that you do on your laptop to an infrastructure. And so you hear a lot of discussion to say, well, if you have data that's already sitting in a big data cluster, like Spark on a distributed storage, you might want to do data preprocessing or augmentation on it. And then finally, this data or this results gets written back to some distributed storage, right? And then you start your machine learning and deep learning job on it. And therefore, that you will see a lot of conversations around, well, let's do data preparation in Spark, but let's do machine learning as well as deep learning on some different infrastructure, right? Where it's unified by having the same storage, and you could access it in an efficient way. Or you could do all of this in a Spark cluster. And so last year and this year, there are talks on a project that Databricks has shared called Project Hydrogen as well, that shows you how to do that. And of course, you could do it in the cloud as well. But then if you take one step deeper, and this kudos to Reynolds for sharing some of his slides, right, is that there are intrinsic differences between Spark as well as a machine learning infrastructure, right? So in Spark, as many of us in this community would know, you have a lot of independent tasks, and you do embarrassingly parallel and massively scalable jobs, right? And in distributed learning, right, many of these times, the tasks are non-independent, so they rely on each other. There's some parallel processing that's going on, but in a nutshell, it's really about trying to optimize communications between all the nodes, right? And so if you put this in perspective, what happens when a job fails, right? In Spark, this is really easy. You just rerun the crash task. But then in distributed machine learning or deep learning, you have to get to a point where you have to rerun all the tasks. And so if you want to reconcile and start doing machine learning and deep learning on a Spark infrastructure, you have to make sure that these two execution models are well taken care of, right? And so this is essentially some of this premise for many of the work that's happening out there that try to combine Spark and machine learning and DL. We're going to share one of this, which is a talk that one of our engineers called Mark Hamilton is going to give this afternoon on MML Spark, meaning providing you with data types as well as a framework, if you will, for doing deep learning on the Spark infrastructure with just a few lines of code, right? And you saw some of this during the keynote yesterday. There's effort happening called Big DL. Horovod Runner is available today in Databricks, right? That allows you to do distributed deep learning training on a Spark cluster really, really quickly. You can get started really quickly. I'm going to show you some of this in details. Project Hydrogen, you saw some of this last year, and I'm sure this year there's a few talks on it. There's a work in Apache called Apache System ML, and many, many other efforts that looks at trying to run, whether it's TensorFlow or machine learning jobs on a Spark cluster, right? So many of these, I encourage everyone to take a look at it. Today, we're just going to focus on two. One is being able to use the ML runtime in Databricks to be able to run distributed deep learning jobs, as well as what's there in MML Spark as well. So MML Spark is essentially a library that we've been building for a while now, right? That combines some of our assets around cognitive service, which is a set of APIs that wraps around pre-trained models, but it makes it available for you to use within a Spark cluster. We include things like Spark serving and a whole bunch of things that you can look at. In fact, this slide should be updated. 2 days ago, this is version 0.17 now. I'm going to show some of this in action. To get to it, you get to Azure/MML Spark. So this allows you to run deep learning right on a Spark cluster. So let's get to the demo. Now, how do you go to MML Spark? Is if you follow this link and you go aka.ms, MML Spark, it will bring you to our GitHub repository. Everything there is open source. If you can't see it, let me just make it bigger. And so if you follow the instruction here, it will show you how do you go about installing it with a whole set of examples from doing really very simple MNIST classification, right, to iris classification, the flower classification, to more complex examples. And it shows you how to get started and install this in a Spark cluster, right? And so if you're going to use this on the Azure Databricks or Databricks, what you do is you get into the Databricks environment. And in this case, you choose a cluster. And this cluster, for example, I provisioned 2 clusters for this experiment. I created a CPU-only cluster. In this case, you see that this is a cluster that uses Databricks 5.2, right, with Apache Spark 2.4. It's running Python 3. And at the same time, these are some of the machines that's available in the cloud that will become the nodes for the Spark cluster. Now, in order for you to use MML Spark, all you need to do is to go to libraries, right, and choose Install New. And if you go Maven, if you enter the Maven coordinates, which is Apache:/MML Spark .16 or .17, and if you click Install, this will then install the MML Spark library to your Databricks cluster. Now, once you are done with that, if you get back, it will actually provide you with a connector that you can use, right, to be able to use some of the tutorials. So if you go through it, you'll find a connector. And so what I've done is the following, right? I have already installed the connector into my workspace. So if I go workspace and if I've gone import, using the URL provided in the aka.ms/mml Spark page, you will actually have a URL with a .dbc extension, and I'll just paste inside here. And once this is done, you actually see a set of tutorials. In this case, you have tutorials for deep learning using the CIFAR-10 dataset. You have tutorials that's doing flower image classification. Or you have tutorials that does transfer learning and so on and so forth. Now, once you have the notebook in this environment, you are ready to run, right? So what you'll see here is these are the standard Spark stuff. But the only difference here is now that you have the MML Spark installed in the Databricks cluster, you can then start importing the MML Spark libraries, right? And I'm not going to run all of this. You'll realize that we have already made available, for example, this flower dataset as a Parquet file. And so this is how the dataset looks like. And one of the things that MML Sparks provide you is it provides you with a bunch of image transformers. Whether you're trying to do rotation, you're trying to do cropping, and so on and so forth, it makes it really easy for you to do all this image augmentation tasks, assuming you're using deep learning for computer vision. Right, we drop some column, and we define a pipeline that consists of all this stage, if you will. Right, so this is the image transformer. This is where we're trying to unroll the image into a whole set of values. Right, we're trying to drop some columns, and then we do logistic regression out of it. So this was a non-deep learning model. We're just treating the image as a series of values. And then moving on, we define ResNet, and we use ResNet as a way, as we all know, ResNet is one of the deep learning architecture. And this becomes another model which we call the deep learning model. And so once this is done, if you continue down the notebook, which is all provided, you'll see that then you can start training it on the Databricks cluster. MML Sparks takes care of all the complexity of getting the right model for you and so on and so forth. And once this is done, of course, you get the results. And of course, we time the, and of course, here we plot out things that you normally do in the Databricks notebook, right? So this is how you use MML Spark. Before I close on this, you actually get a whole bunch of things, including some of the other things that we've shown on classification, integration with cognitive services, and various deep learning examples, including an LSTM example as well. And so using MML Spark, it makes it really, really easy for you to get started with deep learning on Azure. Now, the other demo I wanted to show you is we talk about machine learning and deep learning, or running machine learning and deep learning workload on a Spark cluster, in this case, Databricks. And many a times, ever since the first feed that I showed you about in the beginning of 2017, when Facebook showed that you could do training of a ResNet 50 on Imagenet in an hour, it kicked off a whole revolution in distributed deep learning. And one of the outcomes of that is really a framework called Horovod, right, which will max out your GPU utilization in nodes. And for a while, being able to run Horovod on a cluster, like a Databricks cluster, is really hard just because you have to deal with all the dependencies, you have to deal with make sure the inter-node communication is taken care of. Now, one of the things introduced in Databricks, and this is not just in Azure Databricks, but also the public Databricks as well, is Horovod Runner, right? And so getting Horovod Runner up on the Databricks environment is also really very easy. In this case, you go to a cluster, and I created a Spark AI cluster, but now I choose my runtime, and you could choose the 5.2 or 5.3 runtime. You'll see that I'm using the ML runtime, right? On top of this, of course, I still have Python, but you'll see that one of the things that I've defined here from a worker type perspective is NC6. So NC6 on the Azure public cloud, right, is essentially GPU machines. NC6 runs the Tesla K80s, right? And you see that we've created a Databricks cluster backed by a whole infrastructure of GPU nodes. So once you're done with that, and because you're using the ML runtime, which has all the goodies of ML packages installed on it, getting Horovod to run is really, really simple. So I'm going to use a Horovod runner for TensorFlow, running the MNIST example. So if I were to click on this, and these are all public tutorials that you can use. All I need to do is I could, of course, import whatever relevant libraries, define checkpoint. Now, one other nice thing about Databricks 5.3 is that before 5.3, if you're trying to do a distributed deep learning job, you have to make sure that whatever storage that you're backing it on, you have to be able to fuse them together. So for example, on the Azure blob storage, we had to fuse them together using something called blob fuse. But because if you're going to use blob fuse, you have to twinkle with or play with the init script for the Databricks cluster. Now in 5.3, if you were to use dbfs-ml, it's all done for you automatically. Right? I'm not going to run all of this, but the point here that I'm trying to get to is this shows you your single node code. But in order for you to get to your horovod code, it's really very straightforward. All you need is to define train.horovod, right? Init your horovod on the Databricks cluster, and then all you need to do, which is the last step, is using horovod runner, which is part of the ML runtime, specify the number of nodes you want to run it on, and it takes care of the intercommunication, setting up the node, and getting distributed deep learning to work, right? So hopefully with this, two demos, it helps you understand how you could get started. And in fact, getting started with this, I encourage everyone to play with this. After this talk, it's really, really easy. And so we're going to switch gear now, where Karthik is going to share with you some of the practical experience on things that he has seen running some of this huge big data as well as deep learning workloads. Yeah.
Thanks, Hyong. Hi, everyone. So deep learning is about using lots and lots of data and throwing a lot of computing power at it to train models using the data set that's available. If the deep learning is done in a distributed manner, then one additional variable that needs to be considered is the communication bandwidth that's available between the processes that are involved in deep learning. So what you see in the slide up there are the core elements that influence the effectiveness of deep learning processes, and specifically like distributed deep learning. So here, like, there are different elements that are involved, and deep learning framework is what that brings everything together and interact with these elements either directly or indirectly to help with deep learning. So as users, as end users, most of the times we do not have to worry about all of these elements that are involved. But when you think about an infrastructure where deep learning is done at large scale, you cannot treat these core elements as black boxes or how they interact with them. It is important to understand the role they play in making deep learning effective. So that's why this talk, or the rest of this talk, is about what are the different considerations one should have when thinking about building out a large infrastructure or getting the best out of the infrastructure that is already available, that is currently being used for big data processing. So before I get into the details on the infrastructure considerations, I wanted to spend a few minutes talking about different interconnect options available for communication between GPUs. So the reason I want to talk about that is because if you think about distributed deep learning, as I said, communication is an important aspect of that. And the reason it is important is because in deep learning, one of the key steps that happen in the process is doing the error backpropagation to compute gradient of the loss with respect to the neural network parameters. So in distributed setup, the gradients are computed on different nodes independent of each other, and they need to be exchanged with each other so that the gradients are averaged and then applied to the current weights to come up with the new weights for the next iteration. So if you think about large models with millions or billions of parameters, these gradients can grow up, or exchanging the amount of data that goes between the nodes can get very, very large. And that's why it's very, very important to think about what kind of interconnect options exist to communicate between GPUs and when to use them, and how an infrastructure can enable folks who build these models or train models to make the best use of the interconnect options that are available. So let me start with the interconnect options that are available for communication between GPUs to set the context here. So there are different ways in which CPUs, GPUs, then switches, PCIe switches can be connected with each other. And in the slide, like you see like one possible topology where these are connected. So here we see two CPUs, each connected to 4 GPUs, and there are network, InfiniBand, and the private links are also included. Again, this is just one way to kind of connect these components. There are different possible ways to connect them. And if you think about that, within a node, if there are 2 GPUs that are used for training, they can communicate with each other through using NVLink. So NVLink is a high bandwidth peer-to-peer communication interconnect that's available. If if 2 GPUs are connected using NVLink, this connectivity can be discovered and can be taken advantage of during training. So the other option that one can use when to communicate between 2 GPUs within a same node is GPU direct peer-to-peer technology. So here, the PCIe bus is used to communicate between the GPUs. And the third option listed out there is GPU direct RDMA. And this is the option that is similar to GPU direct P2P. The only difference is that these GPUs are in 2 different machines, and that's where the remote part in RDMA comes into play. So when two GPUs in 2 different nodes want to communicate with each other, they don't have to use standard network sockets. In fact, if there are better options available, like InfiniBand or RDMA over converged Ethernet fabrics available, it's better to make use of those interconnect fabrics as opposed to the standard networking stack. So the advantage with RDMA or GPU direct, whether it's P2P or RDMA in general, is that it is possible to completely bypass CPU, and it is possible to avoid multiple memory copies when you do that. So in the picture in the slide, you see that the no GPU direct options, the data that needs to be transferred is copied from GPU memory to system memory first, one location, and then it is copied to another location in system memory so that it can be accessed by another process that can transfer the data over. In the case of GPU direct, whether it is P2P or RDMA, CPU can be eliminated from the picture, excuse me, and the multiple copies can be avoided. So clearly the advantage with GPU direct is that direct memory access and direct memory transfers are enabled. So that will contribute to effective training, and there won't, essentially we are taking this high bandwidth connectivity option as opposed to the other options that can slow things down. So with all these interconnect options that are available, the question that one might come up with is, does one have to implement code taking all these different interconnect options into consideration? The good news is no. As end users, we do not have to think about all these interconnect options and implement code that takes care of when to pick what or how to make use of one particular option. That is already kind of abstracted out and supported in this thing called NCCL. It stands for NVIDIA Collective Communication Library. So this one allows multi-GPU communication, and it's much better than directly interacting with CUDA layer. So with NCCL, the multi-GPU communication is made easier, and all the collectives, communication primitives that are needed to make the distributed training happen can be supported through NCCL. And NCCL 1 supported multi-GPU within one node. NCCL 2 made it possible to do the same thing across multiple nodes. So essentially, the way it works is that NCCL forms a ring connecting all the GPUs that need to be involved in the communication, and that ring and how the nodes are placed in the ring are used to perform effective communication. And if it's multiple nodes, the concept is the same. Rings are formed, and these rings are connected with each other to kind of go across nodes. So this slide summarizes how Nickel 2 uses. So if it's within a system, it's a peer-to-peer communication using either NVLink or GPU direct P2P. Or if it is across systems, it can use the standard network stack or InfiniBand with remote direct memory access. And depending on what the topology is, Nickel can handle the communication. For example, like in the top right in the slide, you see the connectivity, all the GPUs, the green boxes connected to CPUs through PCIe, and there is no private link between the GPUs. But in the one that is available in the bottom of the slide, there are better connectivity options available between GPUs. So that one, that it's possible to have multiple rings, multiple overlapping rings, and that will be used when the GPUs need to communicate with each other. So with that, this is probably one of the old slides from like the performance done a few years back, but it shows the difference between using Nickel for distributed training versus using MPI and CUDA. So now let's talk about, with that context, let's talk about how to use GPUs in Spark. If you think about Spark has been around for a while, GPUs have been around for a while. So naturally, there have been several attempts to bring together and get the best out of each of those options. And all the attempts that have been done, or all the projects that have tried to bring these things together, they can be broadly categorized into 3 buckets. The first one is about adding native support for GPUs in Spark. So what this means is that Cluster Manager can treat GPU as a first-class resource, and it can allocate GPU resources like the way it allocates a CPU or memory. And this also means that tasks that get scheduled have this first-class notion of the GPU awareness. This is super complicated and a lot of work involved, so it will be a while before this is completely done and made available. In the meantime, there have been workarounds, or other projects have taken different approaches, and those are options 2 and 3 listed out there. So option 2 is about letting Spark kick off this task that knows how to use GPUs. So from Spark point of view, it is completely a black box. It just kicks off this task and let the task use GPU the way it wants. So the only thing Spark does is giving it a GPU. So this can be done either using simple resource counting. If you have 4 GPUs in a machine, just keep a counter of these resources and increment and decrement that counter as the GPUs get assigned or released. An alternative is to use CPU cores or memory as a proxy for this option, as opposed to doing simple resource counting. The advantage is that it works the standard way in which CPU cores or memory get allocated for different tasks. So third option is about implementing code or generating code for the same functionality that runs on CPUs and make it run on GPUs. So this is a little different than option number 2. As I said, option number 1 is ideal, but in the absence of that, there are other workarounds that are in place. So different projects have tried these different options, and each has its pros and cons in terms of flexibility. Like if you go with one option, is it possible to switch over to another option sometime later? That is something to consider when you pick which one to go with, and data management is another consideration. So if you think about like Spark materializing data, the data gets materialized in the memory. And if you're reading data through a deep learning toolkit, that data probably lands in GPU memory, right? So these are completely 2 different things. And if you're thinking about some kind of interop going on between CPU-based or memory-based system like Spark and a GPU code, so you need to think about how the data works between these 2 different memory systems. Multi-GPU execution is another factor to consider when picking the option. So now let's talk about different considerations one should have to have an infrastructure that supports both data engineering and data science. So having a unified analytics platform that involves a technology like Spark has brought together the data engineering and data science team together. So this means that they operate on the same cluster, and the data does not have to be moved around across multiple clusters. So having the cluster locality is very important when bringing these different streams together. And when the other factor to consider when having the data engineering and data science teams work together is how the data is handed off from one phase to the other phase. And sometimes the data preparation that's needed is common for like 3 different or 5 different data science experiments. So in that case, it's important to think about how to reuse the data preparation, the data that is already prepared, to avoid recomputing or reprocessing the data. And in that same context, it's important to think about the data format. What kind of formats are useful when handing off the data from data engineering to data science? So the second category is about job execution. So Hyong talked about some of it as a part of the project Hydrogen introduction. So here, I have listed out some of the other considerations as well. Like gang scheduling is one of the key things. In big data processing, you don't need all resources to be available, and not all tasks need to be started exactly at the same time. But in the case of high performance computing or deep learning, you need all the resources available at the same time, and all the tasks need to be started at the same time. This means that if you don't have something like gang scheduling, you can still use the traditional scheduling resource allocation mechanisms that are available in big data processing, but that would just mean that we are going with a suboptimal workaround. For example, let's say there's a job that needs 16 GPUs, and only 10 GPUs get allocated in the first, let's say, first second, and 6 more GPUs are needed. So until those 6 GPUs are available, the additional 6 GPUs are available, the job cannot be started. And the 10 GPUs that are already assigned are kind of not utilized. They just wait there for more resources to be available. So that's underutilizing resources, especially the premium resources like GPUs. Next thing is the cluster sharing. Cluster sharing, if you're using same cluster for CPU-only jobs and GPU jobs, you need to think about this noisy neighbor effect. GPU jobs are not exclusively GPUs. Depending on what you do in your code, they may use CPUs and the memory in the system to some or large extent. So they can interfere with each other. That is something to consider. MPI versus non-MPI, Hyong touched upon it earlier, so I'm going to skip that. And support for different GPU generations. That is the another thing to keep in mind. So as GPUs evolve, the cluster grows with different GPU SKUs. And when you allocate GPU resources, or when the scheduler or a resource manager manages these GPUs, it is important to see whether it is okay to mix and match these GPU resources, or whether it's important to pick one particular GPU type for a job. Because GPUs, again, like they have different speeds, and they have different GPU memories, and those are the factors to consider in allocation. So InfiniBand and RDMA GPU interconnect options we looked at in detail. The thing to keep in mind when it comes to infrastructure is how to schedule jobs, keeping this topology in mind. And then the goal is to minimize the distribution. In deep learning, it's better to avoid distribution if you can. If you cannot, at least make sure that you can minimize the distribution and pack these tasks together to reduce the communication cost. Repacking is another option, another thing, feature that can help. But at this point, it's mostly a research area. Finally, I want to kind of wrap up with talking about ML pipelines. So having a unified analytics platform like Spark definitely helps, but there are lots of cases where there cannot be one single runtime that caters to all the needs. So it is important to have something that helps that enables use of different technologies and different runtimes in your end-to-end workflow. Data preparation can be in Spark. deep learning can be done in a different infrastructure, and then deployment or the inferencing can be on another infrastructure or platform or runtime. So having a pipeline, machine learning pipeline really helps. I was going to give a demo of Azure machine learning pipeline on how one can use Azure Databricks for data preparation and machine learning cluster, Azure machine learning cluster for doing deep learning, and then deploying a Kubernetes cluster in Azure for doing inferencing. Since we don't have time, I'm going to skip that. So that wraps up everything we have talked about. When it comes to infrastructure, there are so many elements that are involved. It is important to understand what role they play to get the best out of these different infrastructure components, so that your deep learning and distributed deep learning is effective. And it's also, it's more important when you reuse the same cluster for big data processing also. So I hope this talk was useful and gave you insights into different factors to consider. Thanks for attending the talk. Unfortunately, we don't have time for questions, but we'll hang out after the talk if anyone has any questions. Thank you.
Thank you.